All right, so the next topic I'm going to cover is the second order system in general, and just introduction to second order system and how to describe second order systems in transfer function in the form of transfer functions, as well as finding the response of finding the time response of second order systems. So in general, a second order systems a transfer function of a second order system can be described as what you see here: b over s squared plus as plus b. So just note that I have the same coefficient b that I have here also in the numerator. So in general, even if you do not have the form that, for example, here the numerator has the same coefficient b, that's not going to be a problem. What you can do, for example, if you had c over s squared plus as plus b, all you need to do is just to multiply it out. So it's going to be c over b multiplied by b over s squared plus as plus b. So now you just have it in the standard form of a second order systems, and you just have a coefficient. So even if you have a transfer function which does not really have the second order polynomial, which is actually in this form. As an example, just we're actually going to examine one example. It's going to be very simple, so I'm actually going to write it down. All right, so here, for example, as an illustrated example, you see a system with this given transfer function, 1 over 3s squared plus 2s plus 6. And so not only this coefficient 6, you don't also have it, well, you don't have it in the numerator, but also the coefficient of s squared is not 1. So here the coefficient of s squared is actually equal to 1. So the important thing is that the coefficient of s squared here is 3, which is not 1. And so you don't have the same coefficient 6 that you have here in the numerator. But that's not going to be a problem. So what I'm actually going to do is to eventually convert this into standard form. How I'm going to do it? So I'm just going to factor out this 3. So it becomes, in the numerator, s squared plus 2/3 of s plus 2. Then, in order to make numerator to be also equal to 2, I'm actually going to use this trick. So c over b. So I'm just going to multiply it out. So it's just going to be 1 over 2 multiplied by 2 over s squared plus 2/3 of s plus 2. And you also have this 1/3, well, that you're actually going to take it out. So at the end, it becomes 1 over 6 multiplied by 2 over s squared plus 2/3 of s plus 2, which is now in the standard form, obviously. So now we often describe second order system as what you see here: g of s equal to omega n squared divided by s squared plus 2 zeta omega n s plus omega n squared. And that's something that you also saw in linear system. And the reason for that is that this way, if we characterize the transfer function associated with second order system this way, then we can actually define few parameters that have an actual physical meaning. So we're going to actually extensively talk about this in the next couple of lectures, but for now, just know that omega n is defined as natural frequency, and the unit for it is obviously radian per second, and zeta is called damping ratio, and obviously it's unitless. So now if you really want to correspond the coefficient of this transfer function with the ones that we saw in the previous slide, so now this omega n squared becomes your b, and the coefficient of s in the numerator, which is 2 zeta omega n, becomes a. So if you really want to find omega n and zeta directly from a and b, that's going to be very simple, because from this you get omega n, which is equal to the square root of b, and then you just plug this one back into the first one to actually get zeta, which is going to be very simple. So zeta really going to be just a divided by 2 omega n. And omega n, we already defined it, so that was square root of b. So you also have this one. So really, if you have a and b, then you can easily calculate zeta and omega n using these couple of equations. So so it looks like it's slow, so the connection between my tablet and the computer is slow, but you're actually going to see it. So the equation for zeta is a over 2 zeta, 2 square root of b. And in fact, you see here the final equation, omega n is square root of b, and zeta is a over 2 square root of b. So in general, second order systems can be classified based on the location of their poles into three systems: overdamped, critically damped, and underdamped. That's what you see here. And in fact, we might also define the fourth class, which is undamped. So in that case, that parameter zeta is actually going to be 0. But you can also add that one as well. But as for if they are damped, they're going to be either overdamped, critically damped, or underdamped. So now, how do we define based on the location of the poles? It's just going to be very simple. So if you find the location of the poles, meaning just the roots of the denominator of this second order transfer function, then the poles are actually going to be negative zeta omega n plus minus omega n. Okay, yes, so omega n square root of zeta square minus 1. So now, when zeta is greater than 1, if I actually go back to this slide, so when zeta is greater than 1, then I'm going to have then I'm actually going to have two poles that are both real, because zeta squared minus 1 is going to be a positive number. When zeta is equal to 1, then this term is actually going to be 0, so both my poles are going to be the same, just going to be negative zeta omega n. When my zeta is less than 1, then I'm actually, so this zeta squared minus 1 is going to be negative, and therefore I'm going to have two complex poles. And that's exactly what you see here. So when zeta is greater than 1, I have two real distinct poles. So this is called overdamped. So in this case, a second order system behaves similar to first order system, because it's just going to be a combination of two exponential terms. Very simple. And that's exactly what you see here. So in fact, the step response is going to be looking like this. So the combination, so this C is actually your force or steady state response. And these two exponential terms, e to the power of p1t and e to the power of p2t, combined form your natural response. So now when zeta is equal to 1, as we saw in the previous slide, so both poles are actually going to be the same. So it's just going to be negative zeta omega n. And in fact, since zeta is equal to 1, it's just going to be equal to negative omega n. So that's much simpler. Okay. So even here it's going to be negative omega n, because your zeta is simply equal to 1. Okay, so now in this case, the response of the system is going to be an exponential term, e to the power of pt, then a t multiplied by e to the power of pt plus a c term, which is your force response. So that's actually going to be your step response. So so this case is actually called critically damped. So when you have a repeated real pole, meaning that when your zeta is equal to 1, then this is critically damped. When zeta is greater than 1, it's overdamped. And then the final case is when the value of zeta, which is damping ratio, is less than 1. In which case you have two poles, negative zeta omega n plus minus. So you remember we had omega n multiplied by square root of zeta squared minus 1. So now what I'm going to do is, since zeta is less than 1, I'm actually going to make the zeta squared minus 1 to be simply just, so it's just going to be zeta squared minus 1. So it's just going to be minus 1 minus zeta squared. And of course, in this case, this guy is going to be greater than 0. And therefore, I can just take the this negative 1 out of the square, just make it j. And therefore, I end up with two complex poles. And these poles are actually complex conjugates. So this case is known as underdamped case, because you're often going to have what is called overshoot. Okay. So now if you name omega n multiplied by square root of 1 minus zeta squared to be omega d, this is called this is also another natural frequency, but it's called damped natural frequency. And therefore, your two poles can be just rewritten as minus zeta omega n plus minus j. Okay, so now this, I'm sorry, this is wrong. So j omega t. So it's just going to be j omega t. So that's going to be the location of your two poles. Minus zeta n plus minus j omega t. So now, if you compare the step responses of overdamped, critically damped, and underdamped systems, and you also see here an undamped. So, of course, when you're dealing with an undamped system, this is actually representing zeta equal to 0. So you're undamped, and therefore the response is just going to be oscillatory forever. Okay, so it's just going to be an oscillatory response forever. So, but then you have underdamped. So now as you increase the value of zeta, you're first going to have underdamped, then critically damped, which is this, which is actually zeta equal to 1. Then overdamped is just going to be zeta greater than 1. So as you see, this is zeta equal to 0, which is completely sinusoidal, completely oscillatory response. For an underdamped, it could be also oscillator, but eventually it's going to die out. And for critically damped, it's something between underdamped and overdamped. So it's going to look like this. For overdamped, it looks just like a first order system response. So it actually starts, to go up, and eventually it's just going to reach the value of steady state. So now this is the response for zeta equal to 0. Then as you start increasing it, so between 0 and 1, you're actually going to see something like this. At zeta equal to 1, you see something like this. And when zeta is greater than 1, you're going to see something like this. Which now, for overdamped, like I said, that becomes something like a combination of two first order systems. So now if you plot the step response of second order systems in terms of the location of the poles. So now when the poles locations are what you see here. So now when your zeta is actually equal to 0, means this is representing an undamped system. So of course you expect the response to just go oscillating. It's going to oscillate forever. So now when you have so now when you start increasing the value of zeta, but the value of zeta is still greater than 1, but is less than 1, but still greater than 0, then you're going to end up with a pair of complex conjugate poles. Okay, and so the real part of both poles is negative zeta omega n, and the imaginary part is going to be plus minus omega n square root of 1 minus zeta squared. So now this is an underdamped case where you're actually going to see the kind of oscillating response, but the oscillation is going to eventually die out, and the response is eventually going to reach to steady state. And then when zeta is equal to 1, you have a pair of real poles actually located in S-plane like this, and the response is going to look like this. So it is actually going to eventually reach to a steady state with no oscillation. When you have zeta greater than 1, so this is an example of this is classified as an overdamped system where you have a pair of real distinct poles. So as you see, the poles are on real axis, and therefore the response is going to be just like the first order system that you see here. So the last thing I'm going to show you is I'm actually going to slowly make you aware of the command that you can use in MATLAB. For example, you can plot the step response of LTI systems in MATLAB. So in fact, if you just identify the numerator and the denominator of a transfer function, then all you need to do is just to call this this command or this function step, STEP. So the step of num and then actually gives you or just draws or just gives you a plot of a step response. So for example, if you have this transfer function that you're given here, so in order to define the numerator, so you actually put it in a bracket. So all you have to do is just to introduce or to define the coefficients. So it's just going to be 2 and 1. So these are the coefficients of numerator. For denominator, it would be 1, 7, 9, and 1. That's it. And then you just call a step num and then. And if you do this, so just by writing this very simple 3 lines of MATLAB code, then the plot that you get is actually going to be something like this. So it shows you that the system is obviously a stable system because the step response after a finite time is actually going to reach the a steady state value.